think that's the button.
Hello everyone, and welcome to our lesson on thermal physics. I'm Rajesh Desai, and that is Michael David Miller. So, today we are presented with a problem in your slide rocket presentation that says that we need to find the constant pressure in both containers, in which one container has its temperature rise to 100 degrees Celsius and the other has the gas staying at 0 degrees Celsius. Okay, so first, before we even start to solve this problem, we need to have some background information. First, what is an ideal gas? An ideal gas has single atomic molecules. All those molecules are randomly moving, and when those molecules collide together, they do not lose energy. And those type of collisions are called perfectly elastic collisions. Okay? So that is an ideal gas. Now there are properties associated with the ideal gas. Charles' law describes that the volume is proportional to the temperature, directly proportional. In Boyle's law, it says that the pressure of an ideal gas is proportional to 1 divided by the volume. Or you can say that the pressure is inversely proportional to the volume. And in Gay-Lussac's law, it says that the pressure is directly proportional to the temperature. Okay? With all of these laws, for an ideal gas, we can combine them together to form the ideal gas law, which says that the pressure times the volume is equal to the number of moles times the constant times the temperature. Now, what is the constant? The constant, if the pressure is presented in pascals, the constant will be 8.31 joules divided by mole Kelvin. Got that?
Nope.
Okay, let's move on to solve the problem. Hello everyone, and welcome to our lesson on thermal physics. My name is Rajesh Carson Susai, and this is Michael David Mueller.
Hello.
And today we are presented a problem in your slide rocket presentation. It is beneficial that you print out or have this presentation accessible to you. So, yeah, let's move on to the problem. The problem we are presented with is basically we have two containers and we want to find a constant pressure in both those containers, in which one container it has a temperature of 100 degrees Celsius and the other one 0 degrees Celsius.
I'll write it out for you. We also know that the pressure to begin with is 1 atmosphere. And that originally both containers are at 0 degrees Celsius.
Okay. Before we start talking about the problem, let's go over some background information. First, what is an ideal gas law? An ideal gas has specific properties. One being it has single atomic molecules. The other, would you like to write that down?
Okay. Sure, Raj.
Okay, single atomic molecules. Good. The other property being that they all move randomly. There is no specific movement that the molecules are moving. They're just randomly moving around the space. The third being that when they collide, when these molecules collide with each other, they do not lose energy. And these type of collisions are called perfectly elastic collisions. So as Michael is writing right now, the collisions are elastic. And with these ideal gases, there are specific rules that go with the ideal gas. Take it away, Michael.
Okay. There are a few laws that were derived by scientists. Okay. The first is Charles' law, named after Charles. V is proportional to T, and that funny little symbol there means directly proportional to. Boyle's law, named after Boyle, is that P is proportional to P is proportional to 1 over V, or pressure is inversely proportional to volume. And Gay-Lussac's law is that pressure is directly proportional to temperature. Now, if you take these together, knowing that volume is proportional to temperature, pressure is inversely proportional to volume, and that pressure is proportional to temperature, you can form the combined gas law, which says PV equals nRT, where P is the pressure of the gas, V is the volume, N is the number of molecules, and R is a constant, and T is the temperature. Well, actually, N is the number of moles if you're using R, otherwise it's Boltzmann constant, but you don't need to know that. So, in this case, R equals 8.31 joules
Per mole
Kelvin.
And you use this constant only if the pressure is in pascals.
And the volume is in cubic meters.
Yes. Okay, everyone got that? Hello everyone, and welcome to our thermal physics lesson. My name is Rajesh Carson Susai, and this is Michael David Mueller.
Hello.
Alright, today we are presented with a thermal physics problem. So, before we start this problem, we would advise you to print out the slide rocket slides. Don't go. Okay, we cut. Hello, and welcome to our thermal physics lesson. My name is Rajesh Carson Susai, and this is Michael David Mueller.
Hello.
Okay, today we are presented with a thermal physics problem. Before we start, we advise you to print out the slide rocket presentation on the Wikispace website. It is very beneficial and it will help you guide you through this process. Okay, so the problem, which is explained more in the slide rocket presentation, is basically we have two containers, one at 100 degrees Celsius and the other at 0 degrees Celsius. Wait, is that how it starts?
Yeah. Or, no, they start off.
They start off at 0, right?
Okay, we're counting this, but let's see.
They start off at 0, right? I'm pretty sure it starts at.
Yeah.
Hello, and welcome to our thermal physics lesson. My name is Rajesh Carson Susai, and this is Michael David Mueller.
Hi.
Okay, today we are presented with a thermal physics problem. So before we start, we advise you to print out the slide rocket slides that are on the Wikispace website. It'll help you it'll help you go through the process, and it basically, it has a lot more explanation. So, let's start with the problem. We are presented with two containers, both at 0 degrees Celsius. But we want a constant pressure in both containers that will make one container at 100 degrees Celsius and the other at 0 degrees Celsius. Okay? But first, we're going to have to talk about what is an ideal gas.
Oh, there's one there.
Oh, no, that one works. Does that one work? Because a lot of them don't work. Right.
Let's see. Is it working? I don't see the flashing things.
It's not. Wait. Let's see. Is this? Is that?
It's
Yeah,
a-
that is flashing, right? Or is it? No,
No,
it's not flashing.
I think so.
Oh.
Oh, it's
Okay, so what is an ideal gas? Well, the properties of an ideal gas are, one being they have single atomic molecules. The second being all those molecules move randomly. The third being the collisions are elastic. Elastic, which means that when the molecules collide with each other, they do not lose any energy. Okay, and there are laws that have been developed describing ideal gases. So, Michael, please elaborate
okay. So,
so that people can see.
yeah. First law is Charles' law, which says that pressure is, volume is proportional to temperature. The second is Boyle's law, which says pressure is proportional to 1 over volume, or pressure is inversely proportional to volume. By the way, this symbol means proportional to. And the final one is Gay-Lussac's law, which says pressure is proportional to temperature. So these laws can be combined into one ideal gas law, which says PV equals nRT, where P is pressure, V is volume, N is the number of moles, R is a constant, and T is temperature. And in this case, R equals 8.31 joules over moles times Kelvin, which is true whenever you have P in pascals and V in cubic meters and T in Kelvin.
Alright. Now that we have our ideal gas equation, we can use it to help us solve the problem. So, the first step in solving the problem is to find the number of moles. Since n here represents the number of moles, we can move around the equation to solve for n. So, since we want to have the equation to solve for n, we can divide each side by RT. So we have PV divided by RT is equal to nRT divided by RT. Since RT cancels on this side, we have N all by itself. So we get the number of moles is equal to the pressure times the volume divided by the constant times the temperature. Okay?
Okay, and from there, we can plug in the values. And in this case, N is the number of moles in each container in the initial setup. So, from the problem, we have that P equals 1 atmosphere. And here we can use a conversion factor, knowing that 1 atmosphere equals 1.013 times 10 to the 5th pascals, which you can look up in your book or online. So the initial pressure will be 1.013 times 10 to the 5th pascals. Now we need volume and temperature. It says in the problem that the volume in each container is 100 cubic meters, But
It says
for
that
this,
100 cubic centimeters.
oh yeah, 100 cubic centimeters. But to plug in to this equation with this constant, we need it to be in cubic meters. So we use another conversion factor, which is that in each cubic meter, there are 10 to the 6th cubic centimeters. So here we get 100, which is 10 to the 2nd, divided by 10 to the 6th, which is 1 times 10 to the negative 4th cubic meters. Now, we know that there's a common temperature of 0 degrees Celsius, but since we're judging temperature based on absolute temperature, we need a temperature scale called Kelvin, which is defined by the equation temperature in Kelvin equals temperature in Celsius plus 273.15. So 0 degrees Celsius will be 273.15 Kelvin. Now that we have these values, we can plug in to this equation and get m equals 1.013 times 10 to the 5th times 1 times 10 to the negative 4th cubic meters over 8.31 times temperature, which is 273.15. And if you plug this into your calculator, as seen here, you will get hang on just a second. You will get 4.46 times 10 to the negative 3rd moles. Now, that is the number of moles in each container, and since there are two equal containers, the total number of moles will be m total equals twice the number in each container, which will be 8.92 times 10 to the negative 3rd moles. And there you have it. Now we just have to find the number of moles in each container in the next step after.
Now that we have the total number of moles in both containers, we can set up two algebraic equations using the ideal gas equation to help solve for the number of moles in the heated container. So, first equation we can set up is PV equals N heated times the constant times temperature of the first container. And the second equation we can set up is PV equals parentheses N total minus N for number of moles from the heated container all together times the constant times the second temperature.
Okay. And I'll use another color. These equations work because the total number of moles has to stay the same, but since there is a tube connecting the two containers, there are moles being transferred, so we have to find how many are in each container. So if we're solving for the number of moles in the heated container, we can set up this equation and this equation And we know that the number of moles in the second container will be the total number of moles minus those in the heated container. So, knowing the total number of moles, we can solve these two equations. Since PV equals N heated RT1, and PV equals this second one, N total minus N heated times RT2, and PV in these cases are the same because there's a common pressure and the volumes are equal, we can set these two equations equal to each other. N heated RT1, where T1 is the temperature in the heated container, equals N total minus N heated times R times the temperature in the non-heated container, the one that's kept at 0 degrees Celsius. So, first we can write out that T1 is heated to 100 degrees Celsius. The first container is heated to 100 degrees Celsius. So T1 equals 100 degrees Celsius, which equals 373.15 Kelvin. And T2 is left at 0 degrees C, which equals 273.15 Kelvin. Now, we can solve this equation for N heated. Since R is in both sides, we can cancel. And we have N heated times T1 equals quantity N total minus N heated times T2. If we distribute this, we get N heated T1 equals T2 N total minus T2 N heated. So you can see. Now we want to get this entire expression, this equation, in terms of N heated. So we'll bring this to the other side, adding T2 N heated. So N heated, that is T1 N heated plus T2 N heated. Oops. Equals T2 N total. Since this equals N heated times the quantity T1 plus T2, we can divide both sides by T1 plus T2, and we find that N heated equals T2 N total over T1 plus T2. Now, we know T1 and T2. We know N total from the original derivation. So we can plug this in to get T2 equals 273.15 Kelvin. N total equals 8.92 times 10 to the negative third moles. And T1 plus T2 equals 273.15 Kelvin plus 373.15 Kelvin. So you can see. And if you plug this into your calculator, you will get .77 times 10 to the negative third moles. And there, that is the number of moles in the heated container.
Okay, now that we solved for the number of moles in the heated container, we can use the ideal gas equation And we can solve for the pressure because the question was asking what was the common pressure in both those containers. So we can move the volume to the right side to get P alone. Volume cancels out on the left side, and we're left with P equals nRT over V. And T is T1, which is 373.15 Kelvin, and N is from the heated container. So,
It's really small.
yeah, sorry about that, it's small. But we all know it's from the heated container. So it's 3.77 times 10 to the negative 3 moles. So, plugging the numbers in, we get pressure is equal to 3.77 times 10 to the negative 3 moles times the constant, which is 8.31.
Meanwhile, I shall plug this into my calculator.
Yes, while Michael plugs it into his calculator, I will write it out on the board. T1, which is 373.15 Kelvin. And we divide this all by the volume of the container, which is 1 times 10 to the negative 4 meters cubed. So Michael, what is our answer?
Our answer is 1.17 times 10 to the 5th pascals. We forgot the top of the 5.
Sorry, what? Very picky, aren't you, Michael? Karma.
Okay, so there's your final answer. This is somewhat higher than atmospheric pressure, since atmospheric pressure is about 1 times 10 to the 5th pascals. And there you go.
That's the answer.